All right, so for our first presentation today, it's my pleasure to introduce to you the recipient of the 2016 Raymond L. Lindeman Award, Dr. Erin Hotchkiss. The Lindeman Award recognizes a young lead author for an outstanding peer-reviewed paper in the aquatic sciences, and it's given in honor of Dr. Lindeman, whose seminal paper on trophic dynamics was published just after his passing at the age of 27. Erin Hotchkiss is receiving the award this year for her paper, High Rates of Daytime Respiration in 3 Streams, Use of DEL 018 of Oxygen and Oxygen to Model Diel Ecosystem Metabolism. And it was published in 2014 in Limnology and Oceanography. Erin's co-author on this paper is her PhD advisor, Dr. Bob Hall from University of Wyoming. And this paper is certainly a significant contribution to our understanding of the fundamental process of aquatic ecosystem metabolism. And in this work, Erin took a novel approach using oxygen concentrations with oxygen isotopes and combined that with the Bayesian process model to test the common assumption that respiration rates are constant during daytime and nighttime periods. Her findings dispute this and provide strong empirical evidence showing that in fact there are major diel patterns in respiration that aren't explained by temperature alone, and that daytime rates far exceed nighttime rates. And so these insights are really critical to furthering our understanding of basic stream ecosystem processes. Erin completed this work during her PhD at the University of Wyoming. Since then, she's done postdoctoral fellowships at Umeå University in Sweden and also University of Quebec at Montreal. And this fall, she'll be joining the Department of Biological Sciences at Virginia Tech as an assistant professor. So please join me in congratulating Erin Hotchkiss.
All right, thank you, Kim, and thank you to the awards committee. This is a huge honor. I'd also like to thank my co-author, Bob Hall, as well as my current postdoc advisor, Paul Giorgio, for his support in getting this award. So today I want to talk to you a bit about what we know and what we don't know about rapid carbon and oxygen cycling in fresh waters, and also kind of put in a plug for there's still some great scientific benefits to getting out there for all-nighters in the field. And I think we can learn a lot by being with our field sites for long periods of time in the dark. So a question that's motivated a lot of my own research, and I know a lot of the research of people who are here, is trying to understand how biological processes influence the sources, cycling, and fate of carbon and nutrients in ecosystems. And one of the processes I think of quite a lot is ecosystem metabolism. So trying to understand how what's happening within a stream is altering the fate of materials that come in from land in terms of what may be emitted, buried, or transported downstream. And in thinking about metabolism, we know that it's a central property of ecosystems. I'll be talking today about gross primary production and ecosystem respiration. And we know that it controls carbon and nutrient transformations and fate. It's linked with food web energy fluxes. It reflects some combination of landscape, upstream, and internal processes. And when we talk about internal processes, it's also the balance between benthic and pelagic processes, and not just dissolved organic carbon, but particulate as well. And it's increasingly being used as a metric to assess ecosystem health and understand how ecosystems are responding to environmental change. So despite the obvious importance and the popularity of measuring and understanding metabolism, there are still some things that we don't know. This quote from 2005 I think is still highly relevant. We've learned a lot in the past 10 years, but the respiration of aquatic ecosystems is still kind of a big gap in our understanding of the mechanisms behind the role of aquatic ecosystems in carbon cycling. And quite a large reason for that knowledge gap, as with many things, is the assumptions that we have to make in order to estimate metabolism. So there are many, but I think there are two big assumptions that we always come back to when we think about how we estimate metabolism. The first is that we can use measurements of oxygen as a proxy for carbon cycling. And there were some great talks earlier this morning thinking about how that may not always be the case. And also that respiration measured at night is equal to respiration measured during the day. And I'll address this second assumption a bit more. So we have several reasons why this is probably not a great assumption. The first is that we know daytime temperatures are greater than nighttime, and so we would expect for metabolic processes to maybe speed up in response to these higher temperatures. And there have been some approaches to try to scale ecosystem respiration based on temperature, using Q10 or Arrhenius functions to try to get at how respiration may change as a response to temperature. And the second is that we know that processes are changing rapidly over diel periods. Algae respire, and they also leak out organic matter that's a really good food source for microbes. So we might expect to see exudation and rapid consumption and respiration within very few hours during the day that we might miss with this assumption of constant respiration. Okay, so I'll be talking about ecosystem metabolism. This probably isn't new to most of you. But just to kind of orient you to when we're working in running waters, we're thinking about how the change in oxygen over time is a function of GPP, ER, and air-water gas exchange. And we use kind of a logging station, either at one or two sites, where we can estimate high-frequency changes in oxygen and know that that's some combination of what's happening upstream. And you can see here, part of the reason for this assumption about constant respiration is because we have one set of data, oxygen, and at least two unknowns, respiration and gross primary production, and sometimes also air-water gas exchange. And so we have to estimate respiration at night when GPP is turned off, right, to try to get at this one unknown. So we can potentially add another set of data to this, where we can use oxygen isotopes to estimate diel respiration. And we can do this because of the distinct signatures from both photosynthesis and respiration. We know that photosynthesis is creating oxygen at a signature pretty similar to the water, and that respiration is discriminating against the heavier isotopes. So the ratio of 18 to 16 lets us get at these diel changes that we see here. Let's see. Yep. So if we look over 24 hours, we would expect, if biology is happening, to see this diel change in 18O due to both photosynthesis and respiration happening. And I want to stress, and I'll come back to this in a minute, that understanding this fractionation factor that's controlling what we see as the signal from respiration in oxygen isotopes is really important, and we measured this using some dark flow-through chambers to try to get at what might be happening on the benthic substrate in flowing waters. Most of the incubations up to this point had been not flowing waters or just water column, so we're trying to get at better estimates for streams. Okay, so we did this in 3 sites in Wyoming, Red Canyon Creek, which is kind of in the middle of the state, and Kelly Warm Springs and Polecat Creek, which are in Grand Teton National Park. Really ugly places to work, right? And I had some great help in the field, and I also I put this, nice picture of algae here to remind me to tell you that these are pretty productive systems. So we wanted to target, where would we actually see this diel change if it's happening? And Kelly Warm Springs and Polecat especially are quite productive, a lot of algae. So instead of putting up the series of equations, which I've done before, and someone actually asked me for the slide as an April Fool's joke to his students, and so I took that as maybe it's a bit much. So what I want to show you instead is what the model output looks like and give you an idea of what we're doing. So we're looking at both oxygen over time and 18O over time, and we're using this dual inverse modeling approach, where we find the best estimates of metabolism that allow us to model oxygen that hopefully fits the curve of the data. So I'm showing you the line is the model, and the points are the data. And the oxygen we had at 10-minute frequencies, the 18O, I was out there for all-nighters, but I was a little bit lazy. It's only every 4 hours. And yeah, so we estimated GPP and kind of basal ER, so what we would get from just the oxygen model alone, so this assumption that it's constant over 24 hours, and those were shared between the oxygen and the 18O model. And then we have this extra term that in the paper we call diel met, and that is what responded to the diel changes in 18O due to oxygen. And so as I move forward, when I talk about ecosystem respiration from this modeling exercise, it's kind of this basal ER that we'd estimate from O2 alone, plus this diel met that allowed us to get at the magnitude of changes over 24 hours. Okay, so jumping straight to the results. In all of these sites, we found that daytime ecosystem respiration, again, is this basal from O2 and the 18O diel met term added together, was consistently higher than nighttime respiration. So respiration we talked about as a negative flux of oxygen because it's consuming O2. So these more negative values are during the day when we found higher respiration and then lower respiration at night. And this flat line is, for the inverse modeling, we had to shut things off due to light. So there's kind of this embedded light term. But the magnitude of day to night is due to the changes in the oxygen isotopes that we were able to use to estimate diel changes. And if you look at the dotted line, this is what we would get if we scaled respiration based on some kind of Arrhenius function. So temperature alone is not explaining the magnitude of respiration that we estimate using oxygen isotopes. So we're missing something. And while this is a really cool result, and I think can inspire a lot of future work, I know it inspired some future work for me that I'll talk about in just a minute, it also comes with a caveat that your choice of the fractionation factor when you're using this modeling exercise matters a lot. So what I'm showing you here now on the x-axis is the choice of alpha R within the range of values that have been measured in the literature, and this diel met term. And so what you think a stream or marine ecosystem is doing in terms of diel changes in respiration is largely determined by the alpha R that you choose. So having a good idea of what this number is specific to your system, I think, is critically important. So what is driving this higher daytime respiration? We know that it's not just temperature. There's potential that it could be higher oxygen cycling without coupled carbon cycling. So some fraction of this magnitude of the diel swing could be due to photorespiration or the Maillard reaction, and we don't really have a good idea of the role of these processes at the ecosystem level, especially for streams and rivers. And then also going back to the role of primary production, higher daytime algal respiration, or also exudation of dissolved organic matter. And I want to talk briefly about some work that was kind of inspired by the 18O work to better understand what's happening to algal carbon immediately after it's fixed in terms of respiration and exudation, and how that may be fueling this increased daytime respiration that we see in these streams. So to get at the fate of newly fixed carbon, I did a whole stream 13C DIC pulse chase addition, which allowed us to estimate not only the carbon that was fixed, but also the fate of that carbon through respiration, consumption, lost as dissolved organic carbon, and also looking at kind of the residence time of that fixed carbon. And the first fate that I want to talk about is really rapid respiration of newly fixed carbon by algae and associated heterotrophs. What I'm showing you now is, what I want to show you now is looking at distance downstream of where we added the tracer. And in this case, it's the DIC flux as grams of 13C per day. Immediately after the addition ended, but a long enough time to get the tracer through the system, right? So we're not still measuring residual tracer that we added. We saw accumulation of 13C DIC that we can attribute to respiration, so this kind of rapid turnover of fixed carbon. By later that day, that was already in decline in terms of we were seeing less accumulation of 13C respired, and by day 3 it was not detectable at all. So this is a really short-term fate of fixed carbon, thinking about algal respiration. And the second short-term fate that we found that I think also hints at some really important diel things that we're not capturing very well in the way that we measure ecosystem processes is that we saw algal exudation of newly fixed dissolved organic carbon Again, distance downstream from the tracer addition, and now I'm showing DOC flux as grams of 13C per day. And again, this is net. There was probably a lot of exudation that didn't even get to the water column because it's really good organic matter that the microbes just consumed right away, right? So this is a conservative estimate of what's happening. But during the 13C addition, we saw 13C DOC in the water column. And again, about 3 days after we stopped that addition, it wasn't measurable anymore. So it's this really, really rapid short-term response that we know is happening while the algae are fixing carbon. They're also leaking out dissolved organic carbon. So this has kind of left me with perspectives of how we can kind of continue to improve the way we think about how we sample ecosystems and how concentrations and daily rates may sometimes bias our conceptual models of how biological processes are linked to element fluxes. We know that primary production can fuel higher ecosystem respiration during the day, which we're not really capturing with oxygen alone. We know that respiration and exudation are really critical short-term fates. About 30% of the carbon that was fixed was lost due to these processes within just a few days. And these couldn't be detected by sensors alone. So the technology for sensors is really exciting. I've never had to do a Winkler titration to get at diel metabolism, right? And so I appreciate these technologies very much, but I think there's still a lot of things that we can't just get from sensors alone. And we really need a better understanding of linking carbon, oxygen, and of course nutrient cycling at a range of time scales. And so I want to leave you with perspectives that are that I'm taking with me as I move forward. Thinking about some of the most dynamic and understudied processes are those that are varying on sub-daily timescales. And I've listed a few here. Apologies if I've left out your favorite one. But primary production exudation, rapid consumption of superlabile organic matter, we're missing a lot of these with the way that we measure processes in ecosystems. And while they may not always matter to the net balance in terms of elements, I think they're really critical to understanding the mechanisms that are controlling both the fate and the timing of the things that we measure in aquatic ecosystems. Thank you.
Thank you. Given that you've shown the assumption that daytime and nighttime respiration are not the same, and the gross primary production makes that assumption, wouldn't it be better if we just talked about net ecosystem production during the day and respiration at night? And even that is prone to confusion because some people talk about net ecosystem production over 24 hours. So we just talked about the increase in oxygen during the day and the decrease at night. It might be easier.
Yeah, I mean, that could be one way to kind of avoid what we're missing. But I think if we care about things like the diel changes in respiration and exudation, we'd still be missing some of those. I know very dorky and small-scale things, but I think that are of interest for some other processes as well. Yeah.
Thank you.
But, yeah, thank you.